calculating conditional probability from tree diagram. Let us recall what is conditional probability. Conditional probability is a measure of the probability of an event occurring given that another event has already occurred. Here is the formula for calculating conditional probability. So we are saying what the probability of A happening given that B has already occurred, which is given by the probability of the intersection of the two events over probability of the event that has already occurred, right? And this can be understood from this Venn diagram, wherein S represents the sample space, then A and B are subsets. So in essence, by saying we want to calculate the probability that A will happen given that B has already happened, that area is the stripped area, and the B that has happened is the shaded, the whole of B, right? So for us to calculate that probability, we are simply saying, let us calculate the probability of the intersection of the two events A and B over the new sample space, right? This is what it takes. But we need to note that conditional probability restricts or reduces the sample space, as you have seen. Now we are working with the set B or the event B, right? To simply try to calculate this probability. Also, conditional probability can be calculated from information presented in tree diagrams. So in the examples that follow, what I'm simply going to do is I'm going to solve the conditional probability, but using the tree diagram. So in example number 1, in November, the probability of a man getting to work on time if there is fog is 2/5. If the visibility is good, the probability is 9/10. The probability of fog at the time he travels is 3/20. A, calculate the probability of him arriving on time. B, calculate the probability that there was fog, given that he arrives on time. Now, this is a probability problem, but you should be quick to check whether is it a conditional one. And to do that, you realize that there are lots of clues in the question to tell us we are dealing with conditional probability. I'm going to highlight those, right? So the first phase is if there is fog, if the visibility is good, given that he arrives on time. All these short phrases can give you a clue to say the problem we have here is a conditional probability one because of the 3 that I've highlighted. Now, once you have identified that, the next step, which could be, say, your second step, is to define the variables in the problem. Here we are talking of many getting to work. We talk of fog. So those are the major variables that I'm supposed to define. So we let T be the event getting to work on time. Let F be the event there is fog. So that at least if we want the opposite of there is fog, which is there's no fog, we simply play around with the F. If we want to also represent a situation where the person didn't get to work on time, we play with a T, as you shall see. So once you have defined these major variables, the 2 of them, the next thing is to now try to interpret what you are given. That is, write down the notation for the probabilities that we want to find in A and B. This is our A. We are supposed to write this now in terms of the defined notation, and to say calculate the probability of him arriving on time. it simply means probability of T. Now that we know our T is getting to work on time, right? Then the same, calculate the probability that there was fog, given that he arrives on time, right? So now that one is a conditional probability. Using our variables, we are simply saying is probability of F, given that he arrives on time, that is the T. So these are the two probabilities that we are supposed to calculate, and we have symbolized them, which is good. Then as our third step, you need again to interpret what is written in words in the problem itself. We are given this probability, and that probability. Let us write those probabilities in terms of T and F. That is to say, we write down the notation for the three probabilities given in the question, right? So as such, let's start with the probability of a man getting to work on time if there is fog is 2/5. So we should now write this in symbolic form using our variables that we have already defined, right? So this is probability of T given that F has already occurred is equals to 2/5. So in symbols, this is what it means. We go to the next. If visibility is good, the probability is 9/10, right? Now, by saying if the visibility is good, all what it means is that day there is no fog, right? So now using the F, we then come up with F prime, which simply means complement, right? The opposite of F, that is not foggy, right? So to then represent this statement, it all means that we are saying the probability of T given that F prime is okay is 9/10 as given, right? We go to the next. The probability of fog at the time he travels is 3/20, right? To that, we simply write probability of fog is equal to 3/20, because this one is a straightforward probability of fog at the time he travels. That is that. So that is the probability. Now, once we have finished representing all the given information, the three of them, we can now draw a tree diagram. The tree diagram would be something that we are going to discuss first before I draw it. These are the three probabilities that we are given. Now, it is always important that you try to identify the dependent variable and the independent variable, right? And you can only realize that from the given information. I'm given that the probability of T, given that F has happened, is 2/5. Right? If that is the case, then that means F is the independent variable. The dependent is this one. It depends on the occurrence of F. So it's like in the if-then conditional statement, we are saying if F, then T. T can only occur when this has already occurred. So that's the hypothesis and the conclusion. So I'm simply saying conditional statement from conditional probability given. From here, you decide what is the independent and the dependent variable. Once you have done that, then the independent variable is the one that should have the first set of branches in the tree diagram that you are going to draw. That is, there is form, because that's the independent variable, right? Then obviously, the second set of branches getting to work on time, that is the dependent variable. Once you have put this in place, at times all other things will be easy to carry out. Now, as you can see, this is my tree diagram. The first set of branches, the independent variable F, that is fog and no fog. Then the second set of branches are arriving on time or not, right? So what is the next thing is how do we fill the probabilities in the branches, right? You should notice that events at branches are disjoint and exhaustive. That is, they are complementary events, right? For example, I have this set of branches, right? I'm simply saying, if I'm saying they are disjoint and exhaustive, that means the probability of F plus probability of F prime, the answer I expect to get is 1. That is what we call the probability rule of complementary events, right? So if this is the case, then in this equation, you realize that already we are given the probability of F, which is 3/20. That is the one I placed here. So to find the probability that there is no form, or what it means is I'm going to do my algebra here, right? Make probability of F prime the subject, then I subtract from 3/20 to get 17/20. So this is basically how you find the ungiven probabilities on branches, because events at branches are disjoint and exhaustive. Again, to repeat, when we say disjoint, we are saying there's no intersection, right, on the event. When we say exhaustive, that means if we add their individual probability, the answer you expect to get is 1. That is all what it means. So as such, you will see that probability of T happening, given that F has already happened here, is 2/5. To get this, you do exactly like what I did here. Then we come on this, right? Probability of T happening, given that F has already happened, is 9/10, which is what we given here. Then the other one, you do what I've done here to get the other probability. Once this is done, now to know the probabilities following the branches, that is, if F has happened, then we have a T. So it's F and T, or F intersection T, or F intersection T prime, and so on and so forth. This is why now you see that we have a product here of their individual probability, because when we say F and T, we are simply saying we are supposed to use the product rule, right? That is multiplying their individual probabilities. So this is how I came up with these probabilities when I follow the branches separately, right? So at this point, let us now try to calculate the probability of him arriving on time, right? So now we focus where we have T, that is arriving on time. So we have a T here, we have a T here. If we follow the branches like that, we have a F and T. That is what it means, F and T. That is foggy, and he arrives on time, right? Then again, where there's this T, we follow these branches, that is F prime and T. That is F prime and T, not foggy, and he arrives on time. Our task is to calculate the probability that he arrives on time, right? So we have this situation or this situation, right? So the fact that I'm now using the word or, that means these events are mutually exclusive, right? So we add their individual probabilities. That means if I follow this, which is 6/100, that's the probability of F and T, then the probability of F prime and T is 153/200. To get their combined probability, this or this, that means I have to add their individual probability, because these are mutually exclusive events, right? So as such, we are saying probability of T is equal to probability of F intersection T, the first situation, plus probability of F prime intersection T, the second situation, then obviously we substitute, that is 6 over 100 plus 153 over 200. Then we do our algebra, we have 165 over 200. Then that simplifies to 33 over 40. So that is the probability of him arriving on time. Okay, let us go on now to calculate the probability that there was fog, given that he arrives on time, right? This is what we want. We want the probability of F given that T has already occurred. There was fog, given that he arrives on time. This is how you write it in symbolic form. So this alone is telling us this is conditional probability. Then we come up with the formula that we need to find the probability of F intersection T over the probability of T. So the formula then is what I've written here, right? You need also to note that this is a probability. Remember, the fraction of the conditional probability is constituted. The numerator is a probability, the denominator is a probability. Now, to calculate this probability, F intersection T, this is the situation, F and T. That is F intersection T, right? Then the probability of T, we calculated it in A. So all what it means now, copying the same formula, that is that, then the probability of F intersection T, right, is what I'm saying is 3 times 20, 3 over 20 times 2 over 5, right? The probability of T from A, we got it as 33 over 40, right? So now when we substitute, remember this is a fraction and the bar represents division, but we have the proper division sign. So to avoid confusion, simply substitute this bar by the division sign. So we are saying this is 6 over 100. That is this times this, right? 6 over 100. This bar divided by the probability of T is 33 over 40, which is that one. Once you write it this way, then when you change this division into a multiplication sign, you then substitute this divisor by its reciprocal or its inverse, which is 40 over 33. That is denominator becomes numerator, numerator becomes denominator. This is the situation. So with that, then we do our algebra by dividing with common factors, and eventually we realize that the probability of F occurring, given that T has already occurred, is 4 over 55, right? So we have given solution to our 2 problems that we had to solve. But what is important is once you have your tree diagram put, and also you need to remember the issue of the word and or intersection, then you can use the product rule. Then when you use or, that means that is the addition rule of mutually exclusive events, right? The and is the one for independent events, or what is referred to as non-mutually exclusive events. Now, let us look at example number 2. The probability of a maximum temperature of 28 degrees or more on the first day of Wimbledon, that is tennis competition, has been estimated as 3 over 8. The probability of a particular Asian player winning on the first day, if it is below 28 degrees, is estimated to be 3 over 4. But otherwise only 1 over 2. Right, draw a tree diagram and use it to help solve the following. A, the probability of the player winning. B, the probability that if the player has won, it was at least 28 degrees. Right, like in my first example, all what you need to do first is to define the variables, right? But of course, you would have realized that this is a conditional probability question. How? In this problem, the key word in the question to tell us we are dealing with conditional probability is if. That one written in red, right? That is the one that tells us that this is a conditional probability question. Once that is done, then you have to define the variables. Here we are talking of winning and temperature. Those are the two major variables that are at play. So let W be event player wins. Let T be the event temperature 28 degrees or more, right? So if we want the opposite of what we have written, we still be using these two defined variables. So as our next step, we need now to write down the notation for the probabilities that we want to find in A and B using the notation that we have defined. So in A, we are saying the probability of the player winning. So it will be PW, right? Then the B, the probability that if the player has won, it was at least 28 degrees. At least 28 degrees, that means it's the smallest temperature that we can have is 28 degrees or more, right? And if you look at our definition of T, T is the event temperature 28 or more. So the word at least you need to interpret it. That's the smallest that we can think of, nothing less, but anything greater is acceptable. So at the end, that means it's referring to the temperature 28 or more. So to represent that now in symbolic form, we are simply saying probability of T given that W is okay. That means the player has won, right? Then I'm through with the writing of the notation in the problem that we want to solve. The next step would be now we are given probabilities in the problem. We need also to write them symbolically so that it becomes easy to work with them. So in short, I'm saying we write down the notation for the three probabilities given in the question, right? We have 3/8, 3/4, 1/2. We need to write their probability in terms of T and W. We start by the probability of a maximum temperature of 28 degrees or more on the first day is 3/8. Symbolically, it simply means probability of T is equals to 3/8. Right? Then the probability of an Asian player winning on the first day, if it is below 28 degrees, is 3/4. Below. The T is representing temperature 28 degrees or more. Below, that means that is the opposite of that. So as such, we are saying the Asian player winning W, given that the temperature is below, that is T prime, which is 3/4. The T prime is simply representing temperature below 28 degrees. The T is representing temperature 28 degrees or more. Okay, then the probability an Asian player winning on the first day, if it is not below 28 degrees, then not below 28 degrees, right? It's simply referring, if it's not below 28 degrees, it's 28 degrees or more. That is what it means, right? This is why I put the not below, so that you know the keywords and their meaning in the problem. So it will be simply probability of winning given that the temperature is not below 28 degrees or the temperature is 28 degrees or more is 1/2. Okay, I think we have written symbolically the given probabilities in the question. So the next thing now is we can now draw the tree diagram. Right, the tree diagram, this is the given 3 probabilities. Then again, you need to identify the dependent and independent variable. From here, probability of W given that T has happened. So that means the T is the independent variable. If T, then W. W cannot talk of W if T has not occurred. That is all what it means. So that is a conditional statement from the conditional probability given, this one, right? So as such, the first set of branches, temperature, 28 degrees or more, that's the independent variable, right? Second set of branches, player wins, that is the dependent variable, right? Of course, by trying to identify the dependent and independent variable, you notice that if you don't do that, you will never get the correct, what you call probability to fill up your tree diagram. That is the idea, because this is what is given. And you can even try it to say now you interchange, you take temperature 28 degrees or more as your dependent variable, then it will occupy the second set. Surely you are not going to fill up that tree diagram as shown here, right? So that's our independent variable, the dependent. So that at the end, for us, when we look at this, we are saying W, probability of W, given that T has occurred. T has occurred, this is the W. That is what it means. Because this branch is coming from T to get our W. It's because T has occurred, then we get W. Not W, then T. It cannot be like that, right? Because of this. Okay, again, we need to know how to fill the probabilities on the branches, right? As before, we are saying events that branches are disjoint and exhaustive. That is, they are complementary events. And as an example, we take the first branch, that is the branches that I have in the first place. Then if we add their individual probabilities, you should expect to get 1. That is the probability rule of complementary events. Then when you do your algebra, you then make sure that you make probability of P prime, the subject, then 1 minus probability of T, then probability of T we are given is 3/8, you subtract to get 5/8. This is what I have here, right? Then the others as well follow the same pattern, right? We are given that probability of W, given that T is okay, is half. Then you get the other one by subtract from 1. Probability of T having happened to get W is 3/4, which is 3/4. Then the other one subtract from 1 to get this. This is all what is important in terms of filling up the tree diagram after you've successfully decided which variable is the independent and the dependent. If you mess up here, then you have problems in coming up with these probabilities. It won't be easy, right? You can try it. Okay, now, as such, our A, we want to calculate probability of W, right? Probability of W, this is our W, this is our W, isn't it? So it's this or this. So if this is the situation, we have 3/16. If this is the situation, we have 15/32. But these events, this one and this one, they are mutually exclusive. That's why we are saying this or this situation. So we add their individual probability. We are applying the addition law of individual probabilities. So as such, we are adding this, which is representing this T intersection W plus this P T prime intersection W, right? So it will be 15 over 32. Here it comes. 3 over 16, 15 over 32. Then we do your algebra and simplify, you get 21 over 32. That's the probability of winning, right? Let us go on to B. B now is a conditional one. We want to count the probability of T given that W is already okay. That is, the person has already won, but we need to find out the probability of the temperature, right? So with this, since it's a conditional probability, we then come up with the formula probability of T intersection W over probability of W, which is what I have here, right? Probability of TW, you come here, T and W, that is T intersection W, right, over probability of W, but this we have already calculated it in A. So what we need is to divide. For this one, it is 3 over 16. So we then substitute for that 3 over 16, since there's this bar, substitute by the division sign, then divided by 21 over 32, the probability of W. Now substitute the multiplication sign to the division. Then you substitute the divisor by its reciprocal or the inverse. This then it will be 3 over 16 times 32 over 21. Then you do some simplification, you get 2 over 7. That's the conditional probability. So in trying to give a short summary, when it comes to solution of conditional probability, and you are using the tree diagram, what is important is the identification of the independent and the dependent. Don't just draw tree diagram, then you place any variable at random. At times, you might end up not getting the answer. Because in conditional probability, you are normally given some probabilities. So you have to take them into consideration as you draw your tree diagram. Once you are successful in doing that, then everything else will fall into place. And besides, the issue of defining variables is paramount important, because at the end, you cannot keep on writing like the Asian winning the game, time is 28 degrees or more, writing those things in words. Otherwise, you won't finish. And besides, it can end up confusing you. But once you're working with the defined variables, you see that everything will be easy to do, and it will be like a straightforward process. That is what I thought I could share with you.